Today, what we're going to be talking about is electrical power and efficiency. But before we talk about power and efficiency, we need to talk about work. Work is energy to use an object to move something, to change something. So what we do is the symbol is W for work. Makes sense. Now, work is force times distance. Please write these equations down as we come through them, and also their units, because we are going to be switching from American to metric very commonly, because unfortunately the engineering universe works in both American and in metric, so you'll have to learn both. So the metric unit for work is joules, while the US standard is going to be the foot-pound. So let's have you guys do a practice problem. A high school student squats 135 pounds at 15 inches in the course of 2 seconds. How much work have they done? Okay, so it's force times distance. Now, some of you did 135 pounds times 15 inches, and that's sort of right, but we need to turn the inches into feet to be foot pounds, not inch pounds. So that is going to be 15 pounds, divide that by 12, gets you 1.25 feet. Then you can do 135 times 1.25 feet, or it comes out as 168.75 foot-pounds. Now, if you want to change those into metric units, that's perfectly okay. 1 pound is 4.44 newtons and 3.28 feet per meter. And if we did the conversions, 135 pounds comes out as 600 newtons, and 1.25 feet comes out as 0.381 meters. And again, you can multiply those two numbers together and you get the 228.6 joules. These are the same amount of energy, just different units. Now, energy is the ability to do that work. Energy there are different types of sources of energy. There's mechanical energy, like in a leaping frog or moving car, nuclear energy, like in a nuclear power plant or the sun, chemical energy in the food, or burning something, electrical energy, like the electricity or lightning, electromagnetic, like light or thermal heat. Those are all energy sources, and they all are measured in the units of joules. Now, let's talk about gravitational potential energy. Gravitational potential is the potential for gravity to cause work. It hasn't done it yet, but it will. So this person in his left hand, our right side, has potential energy because it has potential to fall. On the other hand, the brick on the left has no potential energy because it's already fallen. It can't potentially fall anymore. So potential energy comes in this equation. And again, write this down. Potential energy is the mass times gravity times height. The mass being in kilograms, gravity being is the gravitational constant, which we'll hear in a second, and then height is always meters. Now, so gravity on Earth is going to be 32 feet per second squared, or 9.8 meters per second. If you're doing in feet and in pounds, you're going to want to use the 32. If you're using meters and kilograms, you want to use the 9.8. Now, here's an important thing. This mg can sometimes be given to you already, and that would be in the form of newtons. So right here, newtons. So this mg can already be done for you. They just took the kilograms of the object and multiplied it by the 9.8 already. The law of conservation of energy. Energy cannot be created nor destroyed. It can only be transformed from one form to another. Chemical energy that you eat goes into the motion of your moving your bike. The radiant energy of the sun hitting a plant turns into chemical energy from the plant. Chemical energy from the car goes into moving the car. Electrical energy from the electricity turns into toasting your food. But here's an interesting fact. Not all of that energy can be transformed. You cannot get more energy out, but you can't even get that. You always have to be less efficient. There is always energy that is lost. And that is where efficiency comes into the standard. Efficiency, symbolized by the Greek letter nu, which is this fancy looking N, has a longer front end than back end, is a percentage of how much energy in to how much out it has. And it's usually always in a percentage. again, write this equation down. Efficiency is energy out over N, and it's most of the time it's multiplied by 100 to give us into percentages. Power can also be used in efficiency. You can say the efficiency of power, which is just power out over power in times 100. So even we can use the power in that same equation. But what is power? Power, symbolized by the letter P, is the rate at which we use that energy or work. And so we can say it's the energy over time. It's how fast did we use it up? Did we go quickly use it up, or did we take the energy over a long period of time? So the power is energy over time or work over time. Its unit is the watt, like a 60-watt light bulb. It's the same thing. So a watt is equal to a joule per second. So when we do watts, we're always going to want the metric unit, not the foot pounds, not the US standard. You can get the watt, you can get power in the standard. It's called the horsepower, but that is a little bit does not make sense. It's not like a foot pound per second. It doesn't work out that way. It's a lot more complicated than that. So we're going to stick with the watt, which is the joule per second. So let's look at the same weightlifter again, a high school student squatting 135 pounds versus 61.2 kilograms, 15 inches over 2 seconds. How much power have they done? I'm going to give you the conversions for that in metrics, so you can do that. All right, so now you have 135 pounds, which is 600 newtons. We're going to put that into our equations, and we know that power is mgh. The mg is already, it's going to be 61.2 kilograms times 9.8 times, now again, we're going to have to do the meters, so the 0.381 meters. But this time we have to divide it by 2 seconds because we have now time in it. So we divide it, and that gives us 114.25 watts. Now let's look at efficiency with power. A winch lifts 1,960 Newton car engine. Notice it's newtons. So that means not pounds or kilograms, that's newtons. So that's already taking into account our mg. I lift the thing 1960 Newton car engine, 2 meters or about 6 feet into 7 seconds. If the winch uses 110 volts of power source and 20 amps of electricity, what is the efficiency of the winch? So we're looking at efficiency. Got our efficiency equation, power out, power in times 100. Our power out we got to figure out was what is coming in and what's going out. Our power in is electricity. We're using electricity, and then we're getting out, physically lifting the engine block out of the car. So it's going to be gravitational potential energy versus electrical power coming in. So our power is mgh times time, or divide by time. And our power in is electrical power. It's like the equation that we've already learned, current times voltage. So we take our power, our mg, which again, I already told you that we accounted for that mg right here. So 1960 newtons, times that by the 2 meters it lifted up, divide it by 7 seconds. That gives us 560 watts worth of electricity. Now its power in is then current times voltage. Our current was 20 times our voltage 110. So 110 times 20 is 2,200. And then we put that as a fraction, 560 over 2,200 times that by 100. And that gives us 25.45% efficiency. These are real numbers that come from this model of a winch. So this winch uses 25% efficient, meaning that you're using 4 times more electricity to lift it in electricity than you're actually getting out of it. And you can't get rid of that because it's mostly done, that 75% of that is lost due to heating of that engine or that motor itself. So if you have any questions, go ahead and ask me when we get to class.